Beginning of the last topic before the midterm. I know it's all very exciting. So we're going to start by talking about different states of matter, and then we'll focus on gases, as you can see from the title. So what are the three main states of matter? And yes, we can go into, plasma and quark gluon and whatever else you want to do, but we're not talking about those, just the three main states. Write them down. And then what I'm going to have you do is there are three beakers you see here on the page, and I want you to draw each state of matter, labeling them underneath with circles to represent the molecules. And 10 circles is probably too much, but let's change it to 6. So have 6 circles in each container, each representing a molecule, and show the difference between the two faces. Now it also says to draw a cap on the one that requires a cap to keep the molecules keep them in the beaker. Label each of those containers with the proper state of matter, and that's part of your homework, so make sure that you have that done to compare with your groups tomorrow. Not the hardest thing you've had to do all year, I understand, but still, let's do it. Now, we're going to talk about gases to start, because those are probably the easiest to start with, but we need to talk about the different properties of gases, and specifically we're going to talk about pressure, temperature, and volume, and that's what this lesson is going to be about, and then you have a little video to watch at the end. So, gas pressure. Certainly it's something we all understand. You blow up a balloon, there's pressure inside keeping that balloon inflated. Everybody's okay with that. But if you think about it down on the absolute molecular level, it's actually that's the sound of the particles banging against the sides of whatever the container is. And those collisions with the walls of the balloon or the flask or the box or whatever it is you have the gas in, that puts a force on the container. And that force over a certain area is the pressure. So gas pressure result of billions of collisions of gas particles inside an object. These collisions put a force on the object. If there aren't any particles, then there can't be any blank. Well, think about what we just said and think about what that must mean. If there are no particles in an area, then there can't be any blank. And that blank is that where there is no blank, that's called a vacuum. Not a vacuum cleaner that works with properties of a vacuum, but a vacuum exactly is where there isn't any. And that's, again, part of your homework. The atmosphere exerts pressure on us every day. The entire atmosphere is above us. How much pressure? Well, you certainly can call it 1 atmosphere or 1 ATM. Don't write ATM in caps, because that means like the thing you get money out of. So that's not, 1 atmosphere. And duh, we live under 1 atmosphere. So remember SDP, standard temp and pressure, right? That was 273 Kelvin. We're going to get to Kelvin in a second. And 1 atmosphere. At different elevations, we have different atmospheric pressures. So if you're at the top of a mountain, there is less pressure. Why? Write down your best understanding as to why there is less pressure. I think we've talked about it once before, but why is there less pressure when you are high up? And why is there more pressure when you're lower down? And even more pressure when you're underneath the water? Let's talk a little bit about units for pressure. Those I'm going to feed you. One is the atmosphere. And for the regions, there's only one other you need to worry about, and that is the kilopascal. There is a connection between the two. They are related in this way. 1 atmosphere equals 101.3 kilopascals, and that is on your reference tables. At the pre-IB level, you do need to know a couple other units. One is millimeters of mercury. So you may hear on the barometric pressure, you may hear, oh, it's 30 inches of mercury. We're not going to use inches, we're going to use millimeters. And it turns out that 760 millimeters of mercury is 1 atmosphere. And it is also equal to 760 torr, which is another unit. Obviously, torr and millimeters of mercury are exactly the same, but torr is just named after somebody. Now, what do you have to do with these? Not much, actually. Just understand that there are different units for pressure. You may be asked to convert between atmospheres and torr, but there's not really much to do. Atmospheres and kilopascals, not much to do there. Okay, these are the 3 main, and then 2 others right here, millimeters of mercury and torr. All right, so that's it for pressure. Moving on to page 3. we're going to talk about kinetic energy, which is the energy of movement and temperature. So for the purposes of the regions, the average kinetic energy and the temperature are exactly the same thing. Oops. Now that is not entirely true. They are technically, mathematically speaking, they are proportional to each other. However, for the purposes of the regions, they are exactly the same thing. So the question is, which of the following four substances have the same kinetic energy? You got to pick two of the four, and I want you to look at them, and you can press pause for a second. I want you to circle the two that you think. All right, now I'm bringing in a special guest. Ben Wolgang is here. Ben, say hi.
Hi, everybody.
Ben was an unfortunate student to have me as a 10th grader, and has to suffer through me again as a 12th grader. But he actually saw these pages of notes, and he's now totally off the cuff going to tell me which of those two samples have the same average kinetic energy. And I'm not going to pause. This is going to be on first take. You think you feel confident about this one, Ben?
Yes, I do.
All right. Which two? See if you guys chose the right two.
1 and 3.
You're right. Good.
That would have been embarrassing.
Awkward pregnant pause, right? Yeah. So yeah, no, that's right. And the Regents loves to trick you with things like this by giving you different amounts of everything. But if you notice, Ben just paid attention to the temperature. Temperature is 273 Kelvin here, 273 Kelvin there. So if the temperatures are in, what scale? Fill that in. That's part of your homework. Then you can relate the average kinetic energies from temperature. Thanks so much, Ben.
You're welcome.
All right. So we have a little bit more to get to. I'm going to press pause for a second so I can say hi to Ben, but I was hoping that he'd join us, so that's good. Hold on. I don't even know if that works. It looks like, no, we're still sharing, I think. Anyway, we'll keep going. So a sample of gas at 400 Kelvin. We're going to keep putting you on the spot?
Sure.
All right, great. He's confident. That's good. He's overconfident, but that's all right. He's okay. A sample of a gas at 400 Kelvin has double the average kinetic energy of a sample at 200 Kelvin. You can't do this in Celsius because part of the reason is that Celsius can go negative, and then what would you do? It would be kind of weird to explain what's double negative 15. You're going to tell me negative 30, but it can't be because they're going lower in temperature and you have higher kinetic energy. So because things are moving faster at higher temperatures. All right. So the king of all temperature scales is
Kelvin.
That's right. Kelvin is what I was going for,
okay.
But that's okay. Table T, trusty table T for your conversions, although you've done this a million times before. Kelvin is Celsius plus 273. And here are 4 review questions for you to just tackle. Won't be too bad for you, I'm sure, tonight. Last up is volume. Defining volume. This is one that you guys have done a million times before, which is it's the space something takes up. And that something can be a solid, a liquid, or a gas. And I want to talk about that because if you put a gas into a bottle, what shape does it take? What volume does it take? And I'm asking similar questions for solids and liquids. And from that, you should be able to fill out this table. Does a gas, for instance, have a definite volume? I'll get you started in saying, no, it does not. It fits whatever container you put it in. And the same thing for the shape. If you put air in a 2-liter bottle of soda, it takes the shape of the 2-liter bottle of soda. If you put it in a closed-off beaker, it'll take the shape of the beaker and fill the beaker. But what I want you to do is use what you know about solids and liquids to go ahead and fill out the rest of the table. You can press pause and do that. Now, once we get to page 4, we get to talk about the mathematics a little bit. We'll do most of this in class. The 3 main variables for gases are, not surprisingly, the 3 we just talked about: pressure, temperature, and volume. And we're going to talk about how they're mathematically related shortly. But what I do want to introduce you to is probably the biggest contribution that Amedeo Avogadro, who lived in Italy, this biggest contribution. But you're going to have, there's a cliffhanger coming because we're running out of time. So you're going to have to check out the next video in order to go ahead and see that. Okay.